Hi, I'm Curt Frederick with OPW Technical Support. Today we're going to be discussing some basic troubleshooting tips for standard conventional dispensing nozzles. We're going to be referring to this document, H15891 PAE, which is a troubleshooting guide that we're releasing for nozzles. In our lab today, we're going to be following basic safety guides. We're going to have protective gloves. We're going to have eyewear. Obviously, when you're at the site, you're going to be utilizing full safety parameters around your work site. You're going to barricade yourself. You're going to make sure that you've got the high visibility wear, the safety shoes, all applicable safety codes that you need to follow at the site. Today we're dealing with a non-flammable liquid. It's a non-hazardous liquid, so we won't have to follow all the safety precautions that you normally would have to follow at a gas station itself. We're also going to be dealing with standard OPW nozzles. This is an 11 AP nozzle. We test 100% of our nozzles for functionality, shut off. At the end of the actual assembly line, we actually have a fixture that gives us a green light to indicate that the nozzle has successfully passed all tests. So with that, we'll go ahead and get started. This is a known good nozzle. This is the way that a nozzle should work. We're testing with the most extreme conditions that we can set our nozzle up for, and that's with a test assembly that you might want to set up and probably will need to set up in the field. All it is standard hardware that you can purchase at any hardware supply store. It incorporates a 3/4 inch T with appropriate fittings and adapters to a pressure gauge. This particular pressure gauge is 0 to 100 psi. We rate our nozzles for a maximum static operating pressure of 50 psi. That pressure should be measured at the hose point, as you see here, not at the shear valve. That is not the correct way to measure accurate hose point pressures. There is a metering valve inside the dispenser that acts as a thermal relief valve, and sometimes that can malfunction, and the pressure that you see at the shear valve is not necessarily the pressure that you're going to see at the hose point. Okay, the first thing we're going to do is we're going to see a normal shutoff of a good nozzle. Here we're at 50 psi static. We're going to open up the nozzle to the full clip position, which should give us a flow rate of about 9.5 to 10 gallons per minute. We'll do that right now. Then we'll let go of the nozzle latch and we'll see a normal shutoff. There's the high clip position. We're at about 9.5 gallons per minute. I'm simply going to release the lever. You can see that the fuel slows to a trickle, then a couple of drips, and that's what we would consider to be a normal operating nozzle shutoff. Orientation of the nozzle is very important. We want to make sure that the nozzle is properly fitted into the vehicle fill neck and that it is oriented in the proper fashion. There is a flow lock device, which is an attitude device, which detects when the nozzle is turned to the point that the spout has gone beyond horizontal. So we want to make sure that the nozzle is properly inserted and fully inserted into the fill pipe. We want to avoid any inverted fueling, which happens when you take the hose over top of the roof of the car. We want to make sure that the nozzle is inserted properly in the fashion that you see in the video here. Okay, what we want to demonstrate now with the 11 BP nozzle is normal shutoff conditions. We're going to do a liquid shutoff at max flow rate of 10 GPM, and then we'll do another one at minimum flow rate conditions, which would be 3 gallons per minute. So we'll turn the pump on now and we'll show you that. Okay, here we're at 10 gallons per minute. And we're going to go ahead and dip the spout of the nozzle into the container. As you can see, the shutoff is crisp, clean, very quick, and complete. Okay, now we're set at 3 gallons per minute. We'll show you a normal shutoff at 3 gallons per minute. As you can see, once again, we get a crisp, clean, quick shutoff at 3 gallons per minute. Okay, there are a lot of different ways for establishing what the flow rate is. This is only one of those ways. What we do and what we'll show in this video is we will time the length of time that it takes to dispense an even 2 gallons of fuel. So we'll begin dispensing, we'll look at the gallons display, and then we'll start the timer once we get to an even number on the display. We'll dispense a total of 2 gallons, and at that 2 gallon mark, we'll stop the timer. We'll show that here. So we're closing in on 1 gallon. When we get to the 1 gallon point, we'll start the timer. And now we'll stop it at 2 gallons, which would be 3 gallons on the display. Okay. So So the time that it took to dispense 2 gallons of fuel is 33.01 seconds. Okay, now that we've timed the length of time that it takes to dispense 2 gallons of fuel, 33.01 seconds, we'll divide that into 120 to give us a gallons per minute. So 33.01 seconds divided into 120 gives us a resultant flow rate of 3.63 gallons per minute. Okay, now what we're going to show you, we're going to demonstrate how the nozzle behaves when it's operating in an environment where it is below what we consider to be acceptable flow rate of 3 gallons per minute. So we'll adjust the valve to the point that the flow rate is substantially below 3 gallons per minute, and then we'll show you how the nozzle responds accordingly. Okay, so here we're operating at about 1 gallon per minute, and we're going to go ahead and dip the nozzle spout. And you can see it was very slow and sluggish to shut off. Once we go below 3 gallons per minute, the ability of that nozzle to shut off is severely hampered because the flow rate that we're sustaining through it is not capable of achieving the vacuum required for an adequate and reliable shutoff. Okay, so what we just saw here was a nozzle that did not shut off in low flow conditions. So that's one of the first things that you'll want to check at the station when you have a nozzle that has a reported non-shut-off failure. We want to see what the flow rate is at the lowest point. So one might easily go out and put the nozzle in a high clip or a wide open flow to see what the flow rate is, but also be considerate of the fact that somebody might have been operating that nozzle in a low clip position, which would have resulted in a minimum flow rate through that nozzle. So that's what we want to check. We want to make sure that the minimum flow rate through that nozzle is at least 3 gallons per minute. Things that can affect that would be dirty filters, debris in the lines, a collapsed inner wall of a hose, anything like that that could result in low flow rate at the nozzle. Okay, on the other side of the coin, we have non-shutoffs in high flow conditions. In today's ever-pressing economy, the desire is to dispense as much fuel as you can in the shortest amount of time possible. So what we see is see people really flirting with that 50 psi mark. At times we even see static pressures going beyond 50 psi, which gives us a flow rate and a flow condition in our nozzle that would exceed the maximum reliable shutoff rate of that nozzle. So we want to make sure that on the high side of the flow rate, we want to ensure that we do not exceed the 50 psi static operating pressure that we demonstrated earlier. Okay, once the nozzle's been removed from the hose point, it's important to drain the residual liquid that rests inside of the nozzle body. With this being an 11A, it's really simple to do. All we do is we depress the lever, and you can see that the fuel just comes rushing out. Okay, this is an 11B nozzle. It's a B-style nozzle, so it has a no pressure, no flow device on top of the nozzle, and it has a loose lever when there's no pressure applied to it. So it's a little more difficult to drain the liquid out of the nozzle body with the 11B. To do it, you take a screwdriver, you lift the lever, you engage the screwdriver underneath the lever, hold the nozzle upright and pry upwards, and there you see the liquid coming out. Okay, sometimes when you're in the field and you've been asked to report to a nozzle failure in the field because the nozzle leaks, it's important to determine the exact point where the leak is occurring. There are lots of spots in the nozzle where a leak can occur. There is inside the lever area, it can leak. Around the body cap here, it can leak. Around the cap here, the B cap, it can leak. It can leak at the junction between the nozzle spout and the nozzle body. More commonly, we get reports of leaking out the spout. And it's important to register a couple of things. First of all, is the liquid leaking out of the actual tip of the nozzle where the liquid comes out? Or is the leak actually coming from the 6 o'clock portion where the aspirator port or the shutoff port is for the nozzle? It's important to be able to determine where these leaks are so that we can better diagnose it both in the field and if that nozzle does get returned back to the factory. In this example, you can see nozzle leaking from the spout tip, and on first glance it might look like the liquid is actually coming out of the liquid portion of the spout, but if you examine a little closer, you can see liquid coming out of the vacuum shutoff or the aspirator port at the 6 o'clock position. What you're seeing here is a continuous leak that doesn't stop for any reason. And if you see a continuous leak that doesn't stop, it should be accompanied by meter creep. What we mean by meter creep is the gallons display of the dispenser will slowly creep in incrementing values for an indefinite period of time. Okay, so here we have a nozzle that has continuous leakage out of the spout tip. and it's accompanied by meter creep. That's very important, because what that basically tells us is that there is something inside the nozzle that is allowing something to go all the way from the hose point or the dispenser through the nozzle and out the spout. So there's a definite possibility of a malfunction inside the nozzle here. It's important to note that the malfunction that you're seeing here is not going to be attributed to a failure of any portion of the spout. So replacement of the spout at this point would probably be pointless. Any condition where you have leakage through the nozzle, out the spout, continuous with meter creep, will require replacement of the nozzle. Okay, what you're seeing here is a replacement spout subassembly for an 11 BP style nozzle. And what we want to show you on this is what we refer to as a bleeder poppet. The bleeder poppet is a small conical device that you see right here, and when you press on it you can see that it moves in and out with spring tension. Occasionally there'll be debris that gets washed through the hose assembly. Maybe it's dirt, debris, maybe somebody incorrectly used thread tape instead of the approved pipe sealant, and the debris tends to make its way through the nozzle and becomes lodged in the bleeder poppet assembly right here. And what this allows is it allows this poppet to stay open, and any residual liquid that would normally be retained inside of the nozzle body would then be allowed to leak out the spout. We'll demonstrate this failure mode now. So we'll shut the nozzle off normally, and you'll see a large amount of the liquid that continues to drain out of the spout tip. It will eventually stop, and it will not be accompanied by meter creep. So here we can see there's no meter creep present at this point. Once we've confirmed that there's no meter creep, that tells us that the internal valves inside the nozzle are working correctly. The amount of liquid that you're seeing out of the spout is attributed to debris hung in the bleeder poppet, and that can be remedied simply by replacing the spout assembly. Obviously, once you remove the spout assembly, if you physically see debris hung in the bleeder poppet, you can simply remove it, and if you want to, with the new set of O-rings, reinstall it inside of the nozzle, retest the nozzle, and see if that fixes it. If it does, you're good to go. If it doesn't, then there could be some other things inside of the nozzle spout subassembly that's lodging that bleeder poppet in the open position. Go ahead and replace the spout. Okay, we'll take a little bit of break from the nozzle troubleshooting, and we'll talk a little bit about what is a very important thing to us here at OPW. That's thread sealant. I know everybody out there loves Teflon tape, thread tape. I know it's easy, I know it doesn't get you messy, but you can take a perfectly good spout and you can turn it into a perfectly bad spout simply by using thread tape that they say never gets through the nozzle, it never gets through the nozzle body. But here's one that came out of our return stock, and you can see, yeah, they do use thread tape out there. Please avoid using thread tape. Only a non-hardening, gasoline-resistant pipe sealant should be used with the nozzle. Please avoid thread tape at all costs. Another negative effect of thread tape is putting the thread tape on the male thread and then threading it into the nozzle body. If too much torque is applied, you've effectively increased the diameter of that male thread. And by forcing that male thread with the Teflon tape on it, you can very easily crack the casting of the nozzle body itself. Nozzles returned under this condition are not honored under any kind of a warranty, so please avoid Teflon tape on threads. Okay, here we're going to demonstrate a nozzle that does not shut off properly. Remember, anytime you're investigating a shut-off issue, make sure that your nozzle is operating within the flow limit requirements that we say. We want flow rate to be at least 3 gallons per minute, and we want the maximum static pressure not to exceed 50 psi. Here we're at about 10 gallons per minute. We're flowing through the nozzle. We're going to dip the nozzle spout now, and you see that the nozzle has not shut off. Okay, here's a little nozzle troubleshooting tip for you, especially in an area or an issue where you've got a nozzle that's consistently not shutting off. Intermittent shut-off problems are a little bit more difficult to diagnose, but if you've got a nozzle that reliably does not shut off, there's a test that we refer to as a bucket test. And in the bucket test, all we're going to do is we're going to slowly allow that nozzle to become immersed in fuel. Initially, we'll start with the tip in, and then we'll slowly immerse that nozzle. As we go down, it'll be pumping, it'll be dispensing, and if at any point we get this nozzle in the liquid that it doesn't and it suddenly does shut off, we've just identified where the leak is. In this particular nozzle, we know where the failure is. We've implemented a cut O-ring in the spout adapter. So as we immerse that nozzle into the liquid, once that liquid reaches the portion of the nozzle where the spout joins the body and the O-ring is located, that nozzle should shut off. That pinpoints where the failure is. If you continue to immerse the nozzle into the liquid and the liquid gets up into this area and shuts off, you know we've got a problem inside the B-cap area. Unfortunately, that's not a repairable item. It would require replacement of the nozzle. And we'll demonstrate that for you right now. So there you can see the shutoff occurred right in this area. That identifies what the problem is, and we know for a fact that there's a cut O-ring in that spout adapter. This nozzle would only require the replacement of that O-ring, and it should be as good as new. Okay, we'll talk about a couple of other issues that we see out there in the field. This is a 12 VW nozzle, but it uses the basic same rack and lever mechanism as all of our nozzles do. And in this particular case, we want to talk about the trigger spring. Now, the trigger spring is located underneath this lever for the hold open mechanism, and it's typically located on the underside of the nozzle right here, and you can physically see that this spring is broken right here. And what that results in is it results in a lever that does this. Normally this lever has resilience in it from the spring. This spring has been broken. This is a warranty item. If the nozzle's in warranty, send it back. It is not a replaceable item in the field. Okay, another thing we want to talk about is abused parts on a nozzle body. I physically saw somebody use a nozzle to beat on a hubcap, and I think we actually found that in our returns department. And here you see a spout tip of a 12 VW nozzle that has obviously been abused. These are non-warranty items, nozzles that have shown significant dents, dings, cracks, mushroom. These are all considered non-warranty items. And they can simply be repaired by replacing the spout assembly itself, not the entire nozzle. So if you have an abused spout out there, don't send back the entire nozzle for an abused spout. Just simply replace the spout. Okay, here we have an 11 series nozzles mounted in a vise. Notice that the vise is only being crimped on the hard portion of the nozzle. It's not crimping anywhere on soft parts of the nozzle. And what we want to talk about in this case is another leak point in the nozzle that we see on occasion, and we refer to that as a packing leaker. As you can see underneath the nozzle, there is a bright shiny stem right here that as we lift the lever, it pushes that stem in and out of the body of the nozzle. On the top of that stem, approximately in this area right here, is where the actual main poppet inside the nozzle resides. As we lift that lever, that stem glides in and out and it lifts that main poppet off of its seat. Now the stem, where it travels in and out of the nozzle body in this area right here, there's a seal there. It's an actual dynamic packing that provides a liquid resistant seal as this stem glides in and out of the nozzle body. Sometimes that packing loses its ability to seal, and we'll have liquid that leaks out of this area right here and will trickle down the rack, and you'll see a visible leak at that point. If you get a condition like this in the field where you can confirm a leak from the stem area, there is no fix for that. That would require replacement of the nozzle. Okay, here we have a side-by-side comparison of an 11A nozzle versus 11B nozzle. And one of the distinguishing characteristics that set one apart from the other is the flat cap that we see on the 11A versus the humpback that we see on the 11B. The 11B, the B mechanism as we refer to it, implements a no pressure, no flow capability within this nozzle. Basically what that says is if I don't have pressure applied at my hose from an active dispenser, then my lever remains loose and I can dispense no liquid out of that nozzle. The 11A doesn't have that capability, and anytime I lift the lever on 11A, I actually open up the main valve inside of the nozzle. NFPA 2012 has set forth new regulations that say in a retail gasoline dispensing facility, you must have either a no pressure, no flow device, in which case a hold open rack is allowable, or you can go with the nozzle that doesn't have that feature, but in this case you're not allowed to have the hold open rack. Also on these two nozzles, we want to demonstrate some other potential leak points. You've got the main body cap here, and then you've got the B cap here. Each of these have exposure to liquid, pressurized liquid. So you could have some leakage out of the body cap, or you could have leakage out of the B cap area or the A cap area. If you experience a leak in either one of these areas, unfortunately that is not a field repairable, and that would require replacement and return of the nozzle. One thing that we also want to talk about that I think gets overlooked in the field a lot as well is the actual O-rings themselves. First of all, don't ever try to reuse old O-rings. Don't save O-rings from nozzles, spouts that you've removed to use at a later date. Always replace the O-rings with new O-rings. Also, whenever you put the new O-rings on the spout, prior to putting them into the spout body, make sure you lubricate those O-rings. Some light grease is okay, some light oil, 3-in-1 oil, motor oil, any kind of a light lubricant around this O-ring is absolutely essential, because if you don't put the lubricant on there, when you insert that nozzle spout into the body, you have a very good likelihood of cutting either one of these O-rings once you insert it. So you can put a brand new spout on a body, and if you cut the O-ring, if you had a shutoff problem before, you've got a shutoff problem now. So make sure that you lubricate the O-rings. Make sure that when you insert the spout into the nozzle body, you do so with a twisting motion as you apply even pressure. The one thing that we don't want you to do is to put the spout in the body, then turn the spout up and bang it on a table like that. Don't do that. That's not the right way to do it. Gentle but firm twisting motion under pressure, and you should feel that spout pop into place. Then align the screw holes and insert the retaining screw to hold it in place. Okay, we've covered a lot. Let's go back a little bit and review some of the stuff that we've done. All of the steps that we've taken are covered in the troubleshooting brochure that you see here. A link at the bottom will take you to the YouTube videos on our website. You can also go to our website directly at opwglobal.com, and you can look at all of this information, including all of the videos that we've taken today.